So in the last class we discussed about the CPT theorem, and in this class we will discuss about a new topic, which is particle and lifetime. So first point is that the lifetime of the particle, lifetime of the particle, lifetimes of particles, also an indication of their force, force of interaction. So if you consider any lifetime of these particles, their lifetime also indicates which kind of force acting between those particles, or if the particle is decaying, okay, then what kind of force of interaction is there? That can be derived from lifetime of the particle. So if the particles are decaying through strong interaction, if the particles are decaying through strong interaction, they usually show very short lifetime, short lifetime, almost, which is almost will be in the order of 10 raised to minus 20 seconds. In the order of 10 raised to minus 20 seconds. So not always 10 raised to minus 20, 10 raised to minus 22, 22 range it can come. So if the particles are decaying through strong interaction, through strong force or strong interaction, then such particles shows a lifetime which is very small, short lifetime, and which will be in the order of 10 raised to minus 20 seconds. And this type of particles also known as short-lived particles. Short-lived particles. Because their lifetime will be very small. Now, if the particles are decaying through, let's say, electromagnetic interaction, such a particle can have a lifetime of the order 10 raised to minus 16 seconds. And if the particles are decaying, the particles are decaying through weak interaction, they will have a lifetime of the order of the order 10 to the power minus 10 seconds. So basically the lifetime of the particle will give you what kind of interactions are happened when it is decaying, or what kind of force is there. If the particles are decaying through strong interaction, then they will be having very short lifetime of the order of 10 raised to minus 20 seconds, and hence they are called as short-lived particles. If the particles are decaying through electromagnetic interaction, then it is having a lifetime of the order of 10 raised to minus 16 seconds. And if the particles are having lifetime of 10 raised to minus 10 seconds, then the interaction will be weak interaction. So if you know the lifetime of the particle, then you can say that which kind of interaction is there. Now there is some class of particles which are called as resonance particles. Resonance particles. So these are the particles which are extremely short-lived. These are extremely short-lived particles, and which will be having a lifetime, which is in the order of 10 raised to minus 23 seconds. So obviously the interaction will be strong interaction. So these particles will be having lifetime which is in the order of 10 raised to minus 23 seconds. They are called as extremely short-lived particles. Okay. So these particles can travel because these particles can have only 10 raised to minus 23 seconds of lifetime. After that, that will decay into some other particles. So only 10 raised to minus 23 seconds we can observe these particles. So within that time interval, they can travel. They can travel only 10 raised to minus 15 meter. It's femtometer range, 1 femtometer range, or about a diameter of proton. Before decay. So these extremely short-wave particles can have 10 raised to minus 23 seconds of lifetime. So after that, it will decay into some other products, some other particles. So before that decay process, they can travel maximum of 1 femtometer, 10 raised to minus 15 meter, or about a diameter of a proton. That much of distance it can travel. Within that distance, they will decay into some other particles. So the time of resonance is analogous to that of an electron. Is time of resonance is analogous to the time of an electron stays in an excited state. So the time of resonance, you can treat that as similar to this electrons which is in the excited state. Initially, if it is in the ground state, then it absorbs some energy and it will go to the excited state. And then it will come back to its ground state. So if you consider that scenario, we are having electron here. After absorbing certain energy, it will go to the excited state. From that excited state, it will be in the excited form. Then it will come back to the ground state with the emission of that radiation. So this state, when the electron is in the excited state, is similar. You can it is similar or analogous to this particular resonance. That particle will be in some state before it decays. So it is like the excited state of electron. That particle will be in some state, and when it will be in this position. For example, in this case, electron will be in this position with some lifetime. After that, only it will come back to this ground state. The same scenario will happen to these extremely short-lived particles. They are extremely short-lived, so they can be in their state, original state, for 10 to the minus 23 seconds. After that, they will decay into some other products. So it is just like the electron which is in the excited state after absorbing this energy. So then it will come back to its ground state with the emission of this radiation. Similar, so if you are having these extremely short-lived particles, so this will be formed with some process, and this particle will be here for 10 to the minus 23 seconds. Okay. After that, it can travel for a distance of 10 to the minus 15 seconds, 1 femtometer of distance, and then it will decay into some other products. It's only this 10 to the minus 23 seconds you can have that particle. After that, it will decay into some other particles, P1, P2, it is. So it is just like the electron which is excited. So here it is the excited state, then come back into the ground state of these particles. So the resonance, time of resonance is analogous to the time of electrons staying in the excited state. So this is the lifetime of those particles, and these are the resonance particles. Okay. So it is analogous to those electrons which is in the excited state. So when that electron is coming back to the ground state, in this particular case, it will be like the resonance particle decaying to other particles after lifetime of 10 to the minus 23 seconds. So strongly decaying particles do not travel far enough to be observed. So their existence is inferred from their products. Okay. Strongly decaying particles, which means that the particles decaying under strong interaction, strong force. So those particles which are strongly decaying particles, they do not travel. They do not travel enough distance. So strong decaying particles do not travel far enough to be observed. Hence, their properties or their existence their existence is inferred from their decay products. What this means, if you consider this case, you will be having this resonance particle up to only this much of distance, which is moving up to this distance. So, and with the 10 raised to minus 23 seconds of lifetime, you have 10 raised to minus 23 seconds of lifetime. So, within this much of short time period, you cannot detect these particles. This resonance particle cannot be detected. So, their presence, we can get their presence only by examining these decay products. By examining these products, you can conclude that these resonance particles are formed. Okay, so by analyzing these P1 and P2, which are the decay particles, okay, so analyzing these decay products from this resonance particle, we can conclude that there is some resonance particle. We cannot directly observe them because it is lifetime is minus 10 raised to minus 23 seconds. So we cannot observe them directly, and they cannot travel much distance, only 1 centimeter it can travel. So detecting these particles are very difficult. So we have to analyze the decay products, and then we conclude that there can be these resonance particles. So their existence is inferred from their decay products. Okay. And the lifetime of strongly decaying particles means that particles decaying through strong interaction is calculated from the variation their effective mass using uncertainty principle. And these particles are often called as resonance. So initially these particles are not considered as particles. So initially it was considered as resonances, because we can have only that mass of these particles. So scientists were not sure whether this state is a particle or not. So they called this particular state or system as resonance. Okay, so they didn't treated that as particles initially. So the lifetime of these strongly decaying particles is calculated from the variation of their effective mass by using that uncertainty principle. Delta E into delta T. This is H cross, considering as H cross for calculation. And then we'll get their mass. So this is the way how we can calculate their masses. Now suppose we take a bunch of pions. Suppose a bunch of ions in this particular case it is pi plus, which are bunch of ions directed towards proton. So what will happen if you are having a bunch of ions which are directed towards protons? So any interaction take place is in this particular process. So we have a bunch of ions, pi plus, which are directed towards protons. So protons are the targets. Is the target. So pi plus. So pi plus, bunch of pi plus is coming, and there are protons which act as the target material. So when they come and hit on these protons or approaches these protons, will there any interaction takes place? That is the question. Whether there will be any kind of interaction. So this particular reaction we can say pi plus, which is interacting with the plus, and we observed that the output of this particular reaction is coming like pi plus plus p plus. So experimentally we observed like this, pi plus plus p plus gives pi plus plus p plus. So at a glance, at first glance, if you consider at first glance, we can conclude that nothing happened because whatever that fissile material, sorry, that the target particles or the projectile, that is pions, which are directed towards protons, so pi plus plus p plus. So both of them are the products also. Or we can say that considering the reactants pi plus and p plus, and they are interacting each other, but when it comes out, this pi plus comes out, there is nothing happening. Where nothing happens, and only that pi plus and p plus we get as the output. So which means that at a glance or at first glance, we can conclude that it can be concluded that nothing happens in this reaction. Nothing happening in this reaction. But when we plot the graph, when we plot the graph which is having the number of ions interacting with the protons. So the plot, when we plot the graph of number of ions interacting with the protons versus kinetic energy of the ions, we will get plot as shown below. So that plot will be like, if you consider the y-axis, let's use this. Consider y-axis. x-axis. Okay. So that graph, this here we have a number of pions interacting with protons. That is in the y-axis, this axis, and here we have kinetic energy of those pions. And if you plot this graph, then it will come like this. So it will come like this. Okay, so it will be like this. So if you plot that graph, where you have number of pions interacting with that protons versus the kinetic energy, then it almost look like this. Almost like this. Okay. So it will be like this. So which means that there is a hum or hill at this particular energy, and this energy is almost at 200 mega electron volt, around 200 mega electron volt at this particular reaction. Okay, and this width of this particular hill will give you delta E at this particular this range of energy, that is delta E. Width of that hill, you can take your full width at F maxima here. So that will give you delta E, and this delta E is approximately around 100 mega electron volt. Okay. And this experiment was first performed by Enrico Fermi. So Enrico Fermi, uh, so he analyzed this graph, or this plot, and reduced some inference as the hill indicate that majority of pi plus, the hill indicates that majority of pi plus, that's pions, actually interacted with the protons momentarily to form a new particle. However, these new particles, these particles are extremely these particles are extremely short-lived. Extremely short-lived, and it decays to pi plus and proton. So this decay will happen very quickly. So those when from this hill, he inferred from this graph that hill represents that more number of pions, pi plus, interacted with the protons, which are the target material. So when they interacted from this pike, this hill, we can say that number of pions with more number of pions which are interacted at this particular energy, that is around 200 megaelectron volt, and he concluded that uh, there can be there is any additional particles formed in this interaction, but these particles which are just formed, which are extremely short-lived, and they very quickly decay into pi plus and p, that is proton. That is what is happening. So this is his inference from this particular graph. So many such particles were discovered, and they are given the symbol delta. So many in this particular case with that delta E energy. So many such particles are discovered, and they are given by the symbol delta. And this particular process, is known as resonance. So comparing this energy delta E of this width, and the maximum number of interacting ions are getting around 200 mega electron volt. So considering that as your maximum and take that full width at F maximum, will get delta E equal to 100 mega electron volt. From this energy analysis, it is found that these particles are nothing but these delta particles. Okay, so many such kind of particles are discovered. And this particular process where you have that creation of new particle and the annihilation, or that particle decay, not annihilation, it is decaying. So that particles decay immediately to the other its decay products within that 10 raised to minus 23 seconds. Such process are called as resonance, and the particles which are formed in this particular process, they are called as resonance particles or extremely short-lived particles. Okay. Now, if you consider this particular interaction, then you can apply that uncertainty principle. So from you can write from uncertainty principle, certainty principle. From uncertainty principle, delta E dot for calculation purpose, we'll just make it equal to h cross h by 2 pi. So delta E from that graph, delta E is around 100 mega electron volt. Okay, so delta T will be equal to h by 2 pi times delta E. So that will give 6.626 into 10 raised to minus 34. So this is in joule divided by 2 into 3.14 into delta E is 100 mega electron volt, 100 into 10 raised to 6 electron volt. Also, in order to change this unit joule to electron volt, I had to divide this quantity, which is in the numerator, by 1.6 into 10 raised to minus 19. So this will give you total of 6.6 into 10 to the power minus 24 seconds. So this is the lifetime of that particles which is just formed in that particular interaction. So that will be in the order of 10 raised to minus 24 seconds. So only 10 raised to minus 24 seconds you can observe that particles. That way it's called as extremely short-lived particles. And after this particular time interval, it will decay into its decay products. Okay. So this particles, this is first observed by Enrico Fermi, and this is in 1950. 1950. And what he did, he took some pions, bunch of pions, and they are directed towards proton charges, and this he studied the interaction and the number of interacting pions with the protons versus energy curve. He plotted that curve, and then from that he analyzed that there is one hill at one particular energy or some energy range. Within some energy range there is a particular hill, and from that hill he inferred the information that uh, there can be some particle creation at that particular point, and that particles are extremely short-lived and they decay into their products. So that products are 5 plus, sorry, yes, 5 plus and protons. Okay, so we cannot observe anything, any change happened in this particular interaction, but in between some particles are formed and they have only 10 raised to minus 24 seconds of lifetime. So they decay immediately or they decay very quickly and become their decay products, which is nothing but pi plus and proton. So that's why that hill is coming. If nothing is happened in this particular case, then there will not be any pi plus particles, pi plus particles which is interacting with those protons. We cannot observe this hill if there is no interaction. But there is interaction with this proton. This pi plus is interacting with these protons, and they that can be observed from this hill. Okay, and that can form new or they can create new particle which are extremely short-lived, again decay into that pi plus n proton. So at a first glance we cannot observe that those particles, but from this analysis, from this particular number of pi plus interacting with protons versus kinetic energy curve, eh, if there is nothing happened, if there is no interaction, then we cannot observe any pi plus which are interacting with the protons, but we observe that it is pi plus which are interacting. How we can observe this? We can use the different analysis we can have here. So that we will discuss in the detecting methods. Okay. Okay, so that is what is happening here, and then he found that he inferred that there can be particles creation, and that particular particle is having that delta E of energy, mass energy, which is nothing but the delta particles, and that delta particles might be created in between those interactions. So which means that the interaction will be like pi plus, which is interacting with that protons, which will give you that delta particles. And then these delta particles are decaying into pi plus and p. Okay, so these are the extremely short-lived particles, which will be here for 10 raised to minus 24 seconds of the order of that lifetime. Okay, and it quickly decay to pi plus and p. So this is what is happening in this particular interaction. And this is not the only extremely short-lived particles. We can classify them, these extremely short-lived, extremely these extremely short-lived particles, short-lived particles. I am not going to write all those particles. I will give you some examples. So this can be classified into two types. One is mesonic resonances, means that a mesonic type of extremely short-lived particles. So these are resonance. Then we have baryonic resonance. Baryonic resonance means that extremely short-lived particles in that baryon group. So in mesonic resonance, we have the angular momentum and parity, which is like 1 minus. And in baryonic resonance, we have the angular momentum and parity, which is equal to 3 by 2 plus. So angular momentum is 3 by 2 and parity is positive. And we can give more number of extremely short-lived particles examples. So for one we can give is rho, that is rho plus, rho 0 and rho minus. These are extremely short-lived particles. So I can call this as rho mesons. Then we have K star. These are kaons, but they are not the original kaons that we just discussed, but these are resonances. Okay, kaon resonances. That's why I put K star. And this in this group we will be having K star plus and K star 0. Another one is that W mesons. W mesons also there. So there are many such examples, etc. I'm just putting some of them. And in the case of baryonic resonance, we have that delta particles that we already discussed. And this group will have delta plus plus, delta plus, delta 0, and delta minus. Then we have sigma star. Okay, these are resonance sigma particles. So this includes sigma star plus, sigma star 0, and sigma star minus. So these are not the sigma particles that we discussed earlier, but these are resonances. That's why I put sigma star. And then similarly, we have cascade resonance particles, cascade star, which is having in this group, which is cascade star minus and cascade star 0. So these two are there in this group, and there are many. So we can have different number of resonance particles, uh, and we are not going to list all those particles, but these are some examples for this type of resonance particles or extremely short-lived particles. Now, these are extremely short-lived particles. How we can detect these particles? That is another question. So there are basically two different type of detection method. So detection methods for extremely short-lived particles. Detection method for extremely short-lived particles. So first one, there are two types. There are two methods. Two methods are there. So the first one will be a beam of particles that we just discussed. A beam of particles just fired at the target, and particles leaving the targets are examined. So that's what Enrico Fermi also did. So a beam of particles, beam of particles fired at a target, beam of particles fired at a target, and the particles leaving the target, are examined. Now, what will happen in this kind of scenario? What are the possibilities? First possibility is that certain number of particles will cross the barrier, cross that target particle, and will be emitted in their original direction with their original energy, like nothing happened. So that is first case, first possibility. That is certain number of particles, will cross the barrier, means that it will cross that target particles and will be emitted in their original direction, with the same energy. Okay? Their energy. So this is the case when nothing happened between those particles. So the incoming particles and target, if there is nothing happened in between them, then those particles will just cross that target, just cross the barrier, and will be emitted in their original direction. So if it is coming in this direction, for example, if you consider this is your uh, particles, beam of particles, this is coming to this particular target. This is your target. So they will just cross this target and comes. Uh, they will be coming in the same direction of in their same direction with the same energy, which means that nothing happened in this particular region. Okay, so nothing happened. That can be one of the possibility, and the other possibility, another possibility is that other particles, some other particles. Okay. So that other particles can be deflected in different direction, or what we can say, or leave with energy different from original energy. Okay, so that is another possibility. There are some particles which will be coming in this group. Some particles may be coming and which can be deflected in different direction from this target. It can be scattered. It can be deflected from this particular target. So they will be having some energy which is less than that of the original energy. Suppose here they are having E1 energy, then here E2 which will be less than E1. So the energy which can be different at this range after that particular deflection. So after deflection, the energy can be varied. Okay, so this is E1, which is not equal to E2. Okay. So the energy will be different. So that is another set of particles. So first set, there is nothing happened. It is just passing through that target. Second case that the particles can be deflected from that target, and the energy will be different after that deflection. And the third set of particles, another possibility is that another possibility that some particles does not leave from the target. Okay, so having been replaced with new particle produced by interaction of missile particle, which means that they are fired. The particles which are fired to those to that target, that is missile particles. So these missile particles and the target particle, they interact. Okay. So some particles that does not leave from the target, having been replaced with a new particle. Okay, so these some particles will not leave from the target, and they will be replaced with a new particle produced by the interaction of that missile particle and target particles. So what will happen in this particular case? So here you will be having number of particles which are coming in this direction, okay, like this, and they will not leave. They just interact with this target, so that you cannot observe them at the output end. Okay, you cannot observe if you consider some kind of detector here, like this. This is your detector. So if these particles are coming, third kind of particles, they will be coming and just hit in this target, but they will not leave to the detectors. Okay, that is the third case. So in that case, what will happen? They interact with this target material and produce new particles. So those particles will not come to the target, sorry, to the detector side. So they will be just interacting with this target, and that will produce new particle in that regime because of that interaction. Okay, so these are the possibilities in this particular detection method. So from that, we can say that if you consider that number of particles interacting versus kinetic energy curve, that I am just of particles interacting with that kinetic energy. So in that case, what is happening? In the first case, it is increasing like this, and then it is coming and it is going like this. So what is happening in this particular range, in this particular region, when the energy is larger in this range, around 200 mega electron volt. Okay, so this is what Enrico Fermi also did. This first method of detection. This is the same procedure what he did. So when he fired those pions, pi plus particles, with to that proton target, here the target is proton, and detector, he used some detector to detect the products, and it is found that when the energy of those pions were at 200 mega electron volt, okay, the detector shows very less number of pions, which means that more number of pions are interacting with the proton, and they are not coming to the detectors. Okay, so at this point, this particular energy level, we have more number of pions which are interacting with these protons, and in other cases we have less number of pions. Okay? So more number of protons which will be interacting with those, sorry, more number of pions will be interacting with those protons at that particular energy, this 200 megaelectron. Okay. So the same method is used by Enrico Fermi to explain that pi plus and p interaction. Okay. So he fired these pi plus particles. These are the missile particles which are coming from, which are fired to this target material, and these missile particles. So he used these ions as missile particles and proton as target, and he observed what is coming out. He observed from this detector. So how many pions are coming out? This is your detector. And it is found that at this particular energy, around 200 mega electron volt, more number of pions are interacting with these protons, which means that number of pions which is reaching at the detector at this particular energy is less. Okay, which means that more number of pions are interacting with the protons at that particular energy. So that these pions are not coming to the detector at that instant. Okay, so that means that these pions are interacting with these protons, and that can create some additional particle, okay, for some 10 raised to minus 23 seconds. After this, that particles, which are nothing but delta particles, they can decay into pi plus and p protons. So proton will be there, and pi plus p can be detected. So within this 10 raised to minus 23 seconds, that much of time, pions will not be there. Okay, so because of the additional particles formed at that particular energy, so more number of pions are formed at this interacted with the proton at this particular energy. So this is the same method or procedure that is followed by Enrico Fermi in his experiment. And second method to detect this extremely short-lived particle, or procedure for such kind of interaction, is that considering this cloud chamber. The second method is by using the cloud chamber. You might have heard of this cloud chamber, and you might have studied this in your lower classes. So we have to use this cloud chamber. So sending beam of pions of a certain energy into a cloud chamber. In this particular example, sending send beam of pi plus particles of certain energy into a cloud chamber, and obtain many photographs. Obtain many photographs. So this is the second method, sending those pions to the cloud chamber and obtain many photographs of that particular interaction. Okay, so we have to take a number of photographs, then we'll get to the track of those particular interaction. So this, let's consider the reaction like pi plus another reaction. So pi plus interacting with the proton, that is that will give proton plus pi plus pi 0. This particular interaction. Okay, and assume that so assume an extremely short-lived particles formed an extremely short-lived particle formed in this reaction. So we are just assuming that one particular extremely short-lived particle is formed. Okay. So in that condition, we can write this pi plus p as some this proton plus some rho. So this rho is the extremely short-lived particles. So plus because it's the plus charge. So there, then this rho plus is decaying into pi and pi z, plus and pi z. So this is what is happening. We are assuming that this rho plus is the extremely short-lived particle which is formed in this particular interaction. So by measuring how much the track, so if you consider the energy of this particular interaction, okay, this rho plus is extremely short-lived particles. This is extremely short-lived particle, and which cannot be, so which can't be observed in photographs. So if they cannot be observed in photographs, how we can claim our hypothesis that this rho plus is formed? If we cannot observe them in the photograph, how we can detect them? Okay. So how we can claim our hypothesis that this rho plus is formed in that particular interaction? So for that, we have to measure their energy. How by applying some magnetic field, external magnetic field, the energy and momentum of the radiation products can be calculated. Now one can easily determine the rest mass of the hypothetical particle, which may have decayed into the two pions. And from that, we now take many such photographs, compare the results, and if the values obtained are the same in all cases, then we can say that the extremely short-lived particles. So how we can claim our theoretical prediction or hypothesis that this rho plus is formed? That can be done by measuring how much the track is deflected by a magnetic field. So by using this, the energy and momentum, of decay, or we can say reaction products instead of particles. Energy and momentum of the reaction products can be calculated. So from this, now one can, if you know what is the energy and momentum of the reaction products, then one can easily calculate the rest mass energy of the hypothetical extremely short-lived particle. So once you know the momentum energy of the reaction products, then you can easily calculate what is the rest mass energy of that extremely short-lived particles from that. So by applying the magnetic field, the external magnetic field will deflect the particles track in that cloud chamber. That photograph you can take. So how much that it will change? That magnetic field is going to change the track. From that you can reduce the energy and momentum of those particles, reaction products. So let's consider like this. Suppose your A particle A is decaying, or I will just write A plus B. These two particles are interacting, and we get C, and this is the short-lived particle which decay into D and E immediately, for example. Okay, so we cannot detect this C, which is the extremely short-lived particle. Okay, so we cannot detect this C in photographs, but we can detect these reaction products, track of these particles and the reaction products. So suppose in that photograph you are having track like this. So this will be forming. So your B will be here somewhere, and then your A is coming. That is the missile particle which are coming and interacting with these B particles, and it will produce you that E and D. So in between this somewhere this C is there, but we cannot detect that. There will not be any track or anything in that photograph. In from that cloud chamber, consider this as this is that photograph of particle interaction, and we cannot detect this C from this photograph. But if you apply some external magnetic field, the particle energy can be shifted, energy and momentum can be deflected. So, so that there will be some shift in your track you can observe in this particular process, and from that you can measure the energy of this energy and momentum of these particles which are formed, which are the products of this particular reaction. And from that, you can say what is the energy, burst mass energy of this C, that is extremely short-lived particles. How? Because this C only uh, decayed into D and E. So all the energy which is associated with D and E will be the energy of C. Okay, rest mass energy of C. So that rest mass of energy of C will be converted into particle D and E plus their kinetic energy. Okay, so kinetic energy of this D and E plus rest mass energy of D plus rest mass of energy of E will be the rest mass energy of C. Okay, so by analyzing what is the energy and momentum of the reaction products and their kinetic energy, one can easily predict the energy of this extremely short-lived particles, and you can say what is the that particle which is formed at this interaction. So this is the second method. So we have to take many such many number of such photographs and analyze each time. Each time analyze these photographs. And suppose in this particular reaction, suppose you are having this interaction. I'll just raise this. So this in this interaction, if you are getting the track of this C, sorry, D and E, if you are getting the track of D and E always same, if the track is always same, if you take n number of photographs and observing the track of this particular decay products E and D, which are same in all the photographs. If you are applying some magnetic field, the track will be shifted, and that also same in all the photographs. Then that will confirm that this C is formed. This is formed, and its decay will be given energy corresponds to this D and E. So it is not a mere coincidence that this D and E will be always having same track and same energy. That is not going to happen if A plus B is going to become C plus D. Sorry, D plus E. So suppose this is happened without forming those extremely short wave particles. So this will not give you always same track. See, energy can be sometimes energy of D can be larger and energy of E will be smaller. Sometimes energy of D is smaller and sometimes that energy of E will be larger. So that can be possible. That energy, kinetic energy can be taken by D or E in this particular interaction. That can be varied in each time if A plus B is going to become D plus E. Okay, but if you are having C which is formed because of the interaction of A plus B, and this C is going to decay into D and E, in that case always the energy of D, energy of E will be the same. Okay, so when you take that photograph, and if you are observing the tracks for all those photographs which are same in all those photographs, then we can say that there is an extremely short-lived particle which is just formed in this particular interaction, but we cannot detect that particular particle because it is very short-lived, extremely short-lived. And photographs also we cannot in photographs also we cannot detect such particles. But from this energy of E and D, we can say if all the photographs is saying same energy for E and D and their tracks are same, then we can say that energy, this particular uh, extremely short-lived particle is formed in this particular. Okay, so I'm not going to write that. You just write it by yourself. So it is not a coincidence that this decay process, decay products, or we can say reaction products, having same energy or same track in all the interactions, all the photographs. Okay, so from that we analyze that the extremely short-lived particles are formed. I will just write it here. It is not a coincidence that the reaction products uh, or I will just rewrite this. It's not a mere coincidence that the energy shared between the reaction products similarly divided among the it is not a coincidence that the energy shared between the reaction products is is similarly divided in all the cases. Okay, so from this you just check the sentence is right or not. So from this we can took such situation as evidence for the creation of extremely short-lived particles. Okay, if that energy shared between those reaction products, which are always same, all in all the cases, if that energy shared between those reaction products are always same, then that is not a mere coincidence. That is not just a coincidence that A and B interacting and E and D always get the same energy sharing. That is not possible. So that is not a mere coincidence every time this will happen. So if in all the cases, all the photographs, we are having same energy for E and D, then that is not a mere coincidence. There should be some additional particle which is just formed and decayed into D and E. In that case, we can have the similarly divided energies for E and D for all cases. Okay. Now I will just show you one another example where we have that proton, anti-proton proton annihilation. So that will be another example of P bar and P interacting, which means that anti-proton and proton annihilation. So in this particular case, 2 pi minus and 2 pi plus and a pi 0 is formed. Okay, so in this particular example, how this photographs look like, that I will just draw here. So in this particular case, if you consider that this reaction, I'm taking, considering this reaction which has happened in that cloud chamber, and we are taking many n number of photographs of that cloud chamber, this particular interaction, then we'll get, let's consider that this proton, this is your antiproton. So this is your antiproton, which is coming in this direction, and which will interact with that proton. That will give you energy. That will give you particles like, sorry, here, this and another way is like this, and then we have after this, we have 5 minus 3 volt. Another case, we have another, and there will be pi 0 in this direction. So this is your pi 0, this is your pi plus, that's pi plus, this is your pi minus, again this is your pi plus, this is your pi minus. So this is going this direction, this is going this direction, this is also going this direction, and this is your pi 0. Pi 0 normally we cannot detect that much easily in that photographs, and this pi plus will become new and plus later. So we are not considering that part, considering this as your photographs. So that photographs will give you like this for this particular interaction. Photograph will be. Now we cannot detect any extremely short-lived particle in this particular photograph. As we discussed, they are very extremely short-lived. They cannot be detected or observed in this particular photographs. Now, if you consider a zoomed version of this photograph with a 10 raised to, let's say 10 raised to 12 times zoomed version. So this is magnification of 10 raised to 12 times. So zooming this particular photograph 10 raised to 12 times, then you can observe. So I am zooming at this junction. This junction I am zooming, making zoom of this particular point. Okay, so that will give me zooming this particular area, this particular area. That will give me the photograph like this. So zooming 10 raised to 12 times. That will give me the photograph like this. You will be having that. So these pions, initial pions will be forming like this, and this is your pi minus. So these are straight lines. Okay. And then immediately a little after, okay, we'll be having that other pions which are going like this. So when you zoom that particular photograph, then you will get this is pi plus, this is again pi plus, and here you have pi minus, you are having pi minus, this is pi minus, okay. Pi bar, this is pi minus, and you will be having that pi 0 coming in this direction. Okay. So what is happening here? You will be having a very short path length here. Okay, you can see, observe that. After that only you are getting these two pi plus and this pi minus. So here there is one extremely short particle which is the omega particle, and the interaction, this interaction will be like p bar plus p going to become omega plus pi minus plus pi plus. And later this omega will be decayed into another pi minus. So here on pi 0 also. Sorry, this one is not pi 0. This is only pi plus and pi minus. And then this omega will be replaced, decayed into another pi minus and pi plus plus pi 0. So this omega is decayed into pi plus pi minus and pi 0. Okay, so this is what is happening in this reaction. So in the initial photograph, you cannot detect anything more than what is this reaction. But if you zoom it into 10 to the power 12 times, then you can observe that there is a very small track that is also there at that junction. And from that, we can understand that one new particle is created, and that is omega, and that omega is decayed into pi minus pi plus and pi 0. And in total, you will get 2 pi minus plus 2 pi plus plus pi 0. Okay, so that's all about the extremely short-lived particles. And the next class we will discuss about the different models for these particles.